Today we're going on a really interesting journey, I think. It connects one of the, well, heaviest physics textbooks out there with light from a star that exploded almost 1,000 years ago.
That's right. We're basically looking at how the deepest ideas about gravity relate to um, a really dramatic cosmic event that was actually recorded by ancient observers.
Exactly. So we've got two very different kinds of sources today.
We do. On one side, there's the cover of Gravitation, the big book by Miss Norner, Thorne, and Wheeler,
MTW.
the absolute classic. And on the other side,
We're looking at the Crab Nebula. It's the aftermath of a huge stellar explosion and, crucially, the ancient records that pinpoint when it happened.
it really sets up our mission perfectly for this deep dive. How does the theory, the math, the physics of gravity actually play out in these, well, incredibly violent stellar deaths?
And how vital is that historical data, that ancient observation, for confirming what our modern physics predicts?
Okay, let's unpack this.
So maybe we should start with the textbook itself, MTW. Right, gravitation, it's hefty, both physically and conceptually.
Oh, definitely. It's pretty much the definitive text on Einstein's general relativity. It fundamentally changed how physicists think about gravity, space, and time.
And that cover is iconic. Just an apple, seemingly.
Yeah, which immediately makes you think of Newton, right? The apple falling from the tree.
The origin story of gravity, sort of.
Sort of. But MTW's cover does more than just nod to Newton. If you look closely, the apple is seen through a kind of magnifying lens.
Mm-hmm.
And inside that magnified view, there are these complex curved lines drawn across the apple.
Okay, so that's the shift. Newton sees it fall straight down a force pulling it. What do the curves mean on the MTW cover?
Well, those curves represent the core idea of general relativity. Gravity isn't really a force in the Newtonian sense. It's geometry. It's the curvature of space-time caused by mass and energy.
So the Earth warps space-time around it, and the apple is just following the curve.
Exactly. Those lines show the path the apple takes through that curved space-time. It's following the straightest possible line, a geodesic, in a curved four-dimensional geometry. It's not being pulled. It's following the shape of the universe right there.
Wow, so the cover is saying, we started with Newton's simple apple, but look closer. The reality is this intricate geometrical dance.
Precisely. It transforms gravity into a question of geometry. And Misner, Thorne, and Wheeler were masters at exploring what that geometry means, especially under really extreme conditions.
Like inside a collapsing star.
Exactly like that. What happens when gravity gets incredibly strong? When immense amounts of matter get squeezed together? That's where the theory really gets tested.
Which brings us, quite dramatically, from textbook diagrams to, well, cosmic wreckage, the Crab Nebula.
Yes, NGC 1952. This is the theoretical concept. It's a real object in the sky. It's the expanding cloud of debris from a massive star that exploded a supernova.
It's basically general relativity's effects made visible on a massive scale.
You could say that. It's the aftermath of gravity winning in the most spectacular way possible.
And the energy involved is just mind-boggling. We know that cloud is still expanding outwards, right? Even now.
Oh, absolutely. And incredibly fast. The sources say it's moving at about 1/300th the speed of light.
1/300th? That's, what, hundreds of kilometers per second?
Easily. And it's been doing that consistently for centuries.
So over the, say, 900 years since the explosion, how far has that debris traveled?
Well, calculations suggest the outer edge has expanded about 3 light years from the center point. 3 light years in 900 years.
That's just staggering. 3 light years. But wait, how are we so sure about that 900-year figure? How do we know exactly when it blew up?
That's the crucial part. We can measure the expansion rate now, but to know the age, we need a starting point. We need to know when the light from that explosion first reached Earth.
And we can't just wind back the clock based on physics alone.
Not with real precision. That's where history comes in. We rely on records made by people who saw it happen.
Ancient astronomers.
Exactly. The supernova that created the Crab Nebula was incredibly bright. So bright, it was visible during the daytime for weeks. It was recorded by observers in several parts of the world, but the most detailed and useful records come from China.
And this wasn't just a casual mention, right? This was official observation.
Very official. The event was first seen and documented in July 1054 AD. These observations were made at the Tung National Observatory in Kaifeng. These were state-employed astronomers.
Wow. What's fascinating here, as you mentioned, is the level of detail. Where does this specific record actually come from?
It's part of the official Chinese historical archives, specifically documents recording unusual celestial events during the Northern Sung dynasty. The text is the Sung Huyao, And the entry is in the Journal of Astronomy, Part 9, Section 53.
So, yeah. So why is that record so valuable today?
Because of its precision and reliability. They systematically recorded the appearance, position, brightness, and duration of these guest stars, as they called supernovae or comets. They noted it appeared near the star Zetatori and was visible for almost 2 years.
So they gave us the exact date, July 1054 AD, and the location. That's the anchor point modern astronomy needs.
It absolutely is. Without that 1054 date, calculating the age, the energy, the expansion velocity of the Crab Nebula would involve much more guesswork.
Yeah.
That historical data point provides a concrete baseline. It's invaluable.
Okay, so we have the theory from MTW describing extreme gravity.
Right. Gravity is space-time curvature.
And we have the precisely dated observation of the Crab Nebula explosion from 1054.
Thanks to the Sung Dynasty astronomers.
Now let's connect them. How does the physics in MTW explain what physically happened in 1054 to create the nebula?
Okay, here's where it gets really interesting. The Crab Nebula came from a core collapse supernova. A massive star ran out of nuclear fuel.
So the outward pressure stopped.
Exactly. And the inward pull of its own gravity, that immense space-time curvature described by general relativity, became completely dominant. The star's core collapsed catastrophically inward.
At incredible speeds, I imagine.
Almost unimaginable speeds. And gravity just kept crushing it down.
Crushing it past the density of normal matter.
Way past the density of a white dwarf star, where electrons resist further compression. Gravity forces the protons and electrons in the core to merge, essentially.
Forming what?
Forming neutrons. The entire core gets compressed into a sphere made almost entirely of neutrons, packed incredibly tightly together. That's a neutron star.
And this idea, a neutron star, it wasn't just discovered recently, was it?
No, the concept is older. Walter Bade and Fritz Zwicky actually predicted them back in 1934.
Really? 1934?
Yeah, they proposed that supernovae must leave behind these super-dense neutron stars. It was purely theoretical then, based on the physics known at the time.
But the Crab Nebula provides the proof.
It provides spectacular proof. Because when we look at the very center of the Crab Nebula today, with modern telescopes,
What do we see?
we see a pulsar, a rapidly spinning, highly magnetized neutron star. It's the crushed remnant of the original star's core.
The direct result of that gravitational collapse.
Precisely. Its extreme density and rapid spin are exactly what you'd expect from that kind of collapse. Think of a spinning skater pulling their arms in the core, shrinks dramatically, so its rotation speeds up immensely to conserve angular momentum.
And how fast is the Crab pulsar spinning?
About 30 times every second.
30 times a second. That's unbelievable.
And it's that spinning neutron star, that pulsar, that's still powering the nebula. It acts like a cosmic dynamo, spewing out particles and radiation that light up the surrounding debris cloud even after 900 years.
So it all ties together. The theory in MTW describes the gravity that causes the collapse. Bade and Zwicky predicted the neutron star outcome.
Right.
The Chinese astronomers recorded the event itself in 1054. And the pulsar we see today is the physical proof, still energizing the nebula.
Exactly. It's a beautiful convergence of abstract theory, historical observation, and, well, dramatic cosmic reality. The physics described by Misner, Thorne, and Wheeler dictates the endpoint, the neutron star, which we observe thanks to the historical baseline.
So what does this all mean? We've basically drawn a line from an apple on a book cover, symbolizing curved space-time.
Yeah, the shift from Newton to Einstein.
All the way to a 1,000-year-old observation from China that recorded the birth of a neutron star.
It really underscores how fundamental physics works across cosmic time and distance. And it shows just how incredibly important meticulous record-keeping can be, even from centuries before telescopes. That ancient data is still critical scientific evidence today.
The universe writes the story, and sometimes, thankfully, someone was there to write it down.
That's a good way to put it. The Sung astronomers captured the timestamp we needed.
Absolutely. And it makes you think. We know the crab debris is still flying outwards at that incredible speed, 1/1300th of the speed of light. The light took time to reach us. The records captured its arrival. If this famous event relied on those Sung Dynasty records, what other explosive, catastrophic events might be hidden in ancient texts from around the world? Events whose light might be reaching us now, or maybe hasn't even arrived yet, that we haven't fully connected the dots on.
That's a fascinating thought. What other cosmic histories might be waiting in the archives, just needing the right modern observation to unlock them?
Something to definitely think about next time you're looking up at the stars.